4.7, Applied Optimization Problems. So in this section, we're going to attempt to use our derivative to find the maximum or the minimum of some certain functions. Now, we're going to have to come up with the functions because these are applied problems. So for example 1, a rectangular garden is said to be constructed using a rock wall as one side, that is this side right here, our rock wall, and wire fencing for the other 3 sides, given here. Given 100 feet of wire fencing, determine the dimensions that would create a garden of maximum area. And then what is the maximum area? Okay, so let's go ahead and use what we know is true, and that is that 2x plus y equals 100. We know that the perimeter has to be 100. We have 100 feet of wire fencing. We have 2 sides that we've labeled x and 1 that we've labeled y. Now we also know that the area is going to be found by x times y. This is the function that we want to maximize, the area function. So if we can write this in terms of all x or all y, that will be great. So let's go ahead and rearrange this. Y equals 100 minus 2x. So that means our area function is x times 100 minus 2x. Now let's go ahead and distribute that. 100x minus 2x squared. Now we want to find the critical points because we want to maximize this. So to find the critical points, we'll take the derivative and set it equal to 0. Oh, not do that yet. Take the derivative, so a prime is 100 minus 4x. Set that equal to 0. That will help us find the critical points. Wrote that too early, which tells us that x equals 25. Now, since this is the only critical point, this is going to have to be our point of maximum area. In fact, if you notice, the area function is, this right here, is a parabola facing down. So that must be the maximum value. All right. So our maximum occurs when the one side, x, is 25, which means that our side y must be 100 minus 2, yeah, okay, 100 minus 2 times 25, which is 50. So we have dimensions of 25 and 50, which makes our maximum area equal to 25 times 50, which is 1,250 feet squared. So here are our dimensions and our area. All right. Example 2. An open-top box is made from a 24-inch by 36-inch piece of cardboard by removing a square from each corner of the box and folding up the flaps on each side. What size square should be cut out of each corner to get a box with the maximum volume? Let's first go ahead and sketch what this means. Okay, we have an open-top box that's going to be made. And we are cutting, well, let's see, each side is 24 by 36. And we are removing a square from each corner. Now, these are all going to be the same size, so we're going to go ahead and say these are x by x. Okay. That's actually what we want to find. We want to know what the value of x is. Now we want to maximize the volume, so let's go ahead and determine a function for volume. Now if you can imagine, what we're doing is this. Here is the bottom of our box, and the dimensions of that box are 24 minus 2x, because we're taking x out from each side. So that is 24 minus x. The width here is 36 minus 2x. And the height of that box, once we fold those flaps up, that's going to be x. All right, well, multiplying that out, we get 864 minus 120x plus 4x squared, and we've still got the x term. So 864x minus 120x squared plus 4x cubed. All right, now, taking the derivative of that to maximize it, we get 12. I'm going to go ahead and rearrange this. 12x squared minus 240x plus 864. Oh, 64. Now, setting that equal to 0 to find our critical points, we factor a 12 out. X squared minus 20x plus 72 equals 0. Now, it'd be great if that equals, factors, okay, to make that equal to 0. It does not, actually. I've already tried that. So let's go ahead and use the quadratic formula. X equals negative b plus or minus the square root b squared minus 4ac all divided by 2a. So that would just be 2. This simplifies to 20 plus or minus, and let's see, that's 400. 288. So 400 minus 288. Let's go ahead and figure that again. 400 minus, that's 112. And let's see, 16 I believe goes into that. Yes, okay, so this is 4 square root of 7 over 2, which means, okay, this is equal to 10 plus or minus 2 square root of 7. So our critical points are at those two values. Let's go ahead and do a sign diagram. We have 10 plus 2 square root of 7 and 10 minus 2 square root of 7. Now, these are each approximately 4.7 and 15.3. So they are both in our domain. Our x value has to be less than 24, but greater than 0. They're both in our domain. So testing some points here, these are both 0. Our derivative is 0 at those points. It's increasing to the left, decreasing in between, and increasing. So it appears that we have a maximum at 4.7, or 10 minus 2 square root of 7. So we have a maximum volume of something at x equals 10 minus 2 square root of 7. Now, evaluating that, we get 1825.3 feet cubed. So there's our maximum volume. And if the side we cut out is 10 minus 2 square root of 7, that would be it. So actually, this question is asking for the value of x there. So 10 minus 2 square root of 7. Want to know what size square to cut out. But our maximum volume would be 1,825.3 feet cubed, approximately. Number 3. An island is 2 miles due north of its closest point across a straight shoreline. A visitor is staying at a cabin on the shore that is 6 miles west of that point. All right, let's go ahead and see if we can draw this. We've got an island is 2 miles due north, and a visitor is staying at a cabin 6 miles west. All right, so he's staying 6 miles west on a straight shoreline. The visitor is staying at the cabin. Okay, the visitor is planning to go from the cabin to the island. Suppose the visitor runs at a rate of 8 miles per hour and swims at a rate of 3 miles per hour. How far should the visitor run before swimming to minimize the time it takes to reach the island? All right, so the question really is, at what point along the shore should he start swimming? That's really the question. So what we want to know is how far along here, at what point, how far he should run before he starts swimming. Well, that leaves this value over here at 6 minus x. All right, so we know the rate that he runs and the rate that he swims. We really are interested in the time, though. So the time spent running is going to be equal to the distance divided by the rate. So the time running is x over 8 in our case. the time swimming is the distance divided by the rate. And he swims at a rate of 3 miles per hour, so we're dividing by 3. Now the distance there is given by the Pythagorean formula, Pythagorean theorem, the square root of 6 minus x squared plus 2 squared, so plus 4. All right, now the time total time here is going to be the sum of these two. Minus x squared plus 4 over 3. Now, to minimize the time that it takes to reach the island, we need to take the derivative of that function. All right, so t prime equals 1/8 plus, now let's go ahead and treat that as the 1/2 power. So bringing that down, we get 1/6, and that is 6 minus x squared plus 4 to the negative 1/2. Subtracting 1 there. Using our chain rule, we get times 2, 6 minus x times negative 1. Using our chain rule twice there. Alright, this is equivalent to 1/2 minus 6 minus x, 6 minus x, and we'll have a negative because of that negative 1 down there, so we have the minus. Alright, 3 square root of the 2 and the 1/6 there. 3 square root of 6 minus x squared plus 4. And we want to set that equal to 0. Alright, well, that means 6 minus x over 3 square root of 6 minus x squared plus 4, no parentheses, equals 1/8. Alright, so multiplying that out, we get, let's see, 8 times 6 minus x equals 3 square root of 6 minus x squared plus 4. Now you might be curious as to why I'm not multiplying that out, but you see how we have the two 6 minus x terms in there? It's going to be to our advantage to keep the 6 minus x factored out there. All right, so if I go ahead and square both sides, we get 64 6 minus x squared equals 9 6 minus x squared plus 4 there. And if I go ahead and distribute that 9, because I've really got this, 9 6 minus x squared plus 36 equals 64 6 minus x squared. If I combine those terms together, I'm going to have 55 times 6 minus x squared equals 36, making 6 minus x squared equal to 36 over 55, and x is going to be 6 plus or minus 6 over the square root of 55. Now let's use a sign diagram here. We have our values of 6, and actually our function is restricted here from 0 to 6 because the distance that the man can run, or the visitor can run, is between 0 and 6. They can't run any farther than 6 miles for what we're trying to accomplish. So that means we have these two values, 6 plus or minus 6 over square root of 55. And in fact, 6 plus the square root of 55, or 6 plus 6 over the square root of 55 is outside of our domains, outside of 6. So you're only interested in 6 minus 6 over the square root of 55. Now at that point, our derivative is 0. We are decreasing prior to that and increasing after. So we have a local minimum here. So the distance that he needs to run is approximately 5.19 miles. And that would minimize our time. Now we're not asked what the time is, so I don't need to evaluate this into our time function, but that is how far he needs to run. All right, example 4. Owners of a car rental company have determined that if they charge customers P dollars per day to rent a car, where P is between 50 and 200, the number of cars N that they rent per day can be modeled by the linear function N of P equals 1,000 minus 5P. If they charge $50 per day or less, they will rent all of their cars. If they charge $200 per day or more, they will not rent any cars. Assuming the owners plan to charge between the 50 and the 200 per day to rent a car, how much should they charge to maximize their revenue? What we need is a revenue function here. And in this case, our revenue function is given by R equals, in fact, this is in terms of price. So R of P equals price times N of P. Well, our price is just our variable, and N of P is 1,000 minus 5P. So our revenue function is 1,000P minus 5P squared. Now, taking the derivative of that, we have 1,000 minus 10P, and setting that equal to 0, we see that the price must be 100. Okay, now let's do a sign diagram, and actually we're restricted on our domain. 50 to 200. We have this value at 100. Now it is increasing between here, 0, and decreasing. So we must have a maximum revenue. Erase that. At a price of $100. Okay. Number 5. A rectangle is to be inscribed in the ellipse x squared over 4 plus y squared equals 1. What should the dimensions of the rectangle be to maximize its area? And then what is the maximum area? We want to know both of those. Let's begin with a graph here. So this is an ellipse with a major axis of 4, or 2. It's elongated along the x-axis. All right, so if we are inscribing a rectangle, okay, every point here where our vertices can be is x, y, and if you notice, our area is going to be 2x times 2y. That is, this distance is x, and so the length is 2x. And similar process for this. So the total width is 2y. Alright, so our area is 4xy. Now if we rearrange this equation here, y squared equals 1 minus x squared over 4. We take the square root of both sides. Y equals square root of 1 minus x squared over 4, which makes our area formula 4x square root of 1 minus x squared over 4. Now let's go ahead and combine those two right there. Square root of 4 minus x squared over 4. Now I'll do that because that will simplify this to be 2x square root of 4 minus x squared. Square root of the 4 is 2. That combines there. Now let's find the derivative of our area function. All right, well, the derivative of our first term is 2. And we leave the second alone, so 4 minus x squared to the 1/2. I'm just going to leave that there. Plus 2x times the derivative of that second term, so that'll be times 1/2. 4 minus x squared to the negative 1/2 times negative 2x. So that would be 2 square root of 4 minus x squared plus minus 2 x squared, let's see, negative 2, negative 1/2, yeah, negative 2 x squared over 4 minus x squared, and that's the square root of that term right there. Okay, now if we set that equal to 0 and then clear our fractions, okay, that would be if we multiply by the square root of 4 minus x squared, we get 2, 4 minus x squared minus 2x squared equals 0. Alright, and we can group that together to be negative 4x squared plus 8 equals 0, meaning x equals 2, plus or minus the square root of 2. There we go. Alright, now let's look at a sign diagram for this. Oh, and we're restricted again. In real world things, we tend to be restricted from 0 to 2. And we have this point, square root of 2. Now, negative square root of 2 is outside of our domain. 0 there, it's increasing, then decreasing, which means we have a maximum at the square root of 2. So our length is 2 square root of 2. Our width is 2 times 1 over square root of 2. Okay, by evaluating that in there, which that's the square root of 2, which means that our area, our maximum area, is 4. So we have a maximum area of 4 at a length and a width given there. All right, our last question. A rectangular box with a square base, an open top, and a volume of 216 inches cubed is to be constructed. What should the dimensions of the box be to minimize the surface area of the box? What is the minimum surface area? We'll go ahead and draw this out. Okay, that right there. Okay, there's our box. Now this is has a square base, which means we have got x, and our height is another variable y. Now our surface area, is 4xy. That is our 4 sides. This is xy, 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 and xy, plus the base here, because it's an open top. So plus x squared. And we know that our volume, which is x squared y, is equal to 216. We want to minimize the surface area, so we're going to use the volume function there to isolate a variable. So let's go ahead and say y equals 216 over x squared. So this makes our surface area equal to 4x times 216 over x squared plus x squared. So 864 over x plus x squared. Now let's take the derivative of that function. Surface area prime, let's call it S. And that is going to be negative 864 over x squared plus 2x. Now setting that equal to 0. Find our critical points. Now let's clear our fractions. Clearing our fractions, we get negative 864 plus 2x cubed equals 0. and x is going to be 6 times the cube root of 2. Now, our value of x can range anywhere from 0 to infinity. So let's go ahead and make a sign diagram. Okay, restricting it at 0, and we've got our 6 cube root of 2, and the function is decreasing prior to 6 times cube root of 2 and increasing afterwards. So that has to be our minimum. So finding our y value, our y is 3 times cube root of 2 using our x squared, or y is 216 over x squared. And our maximum, or our minimum volume is 108 times the cube root of 4 inches cubed. Okay, and that is the end of this section.